Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are moving to the next unit, which is the one shot of the unit C, and which is electromagnetic radiations. We already covered the one shot of unit A and unit B. Today we're doing the unit C, and tomorrow we are doing the unit D, and then we're done with the one shots. And then you have a diploma on 22nd June. I hope you are ready for that. If not, so you can watch these one shots and you will like all doubts can be clear in that. So let's start with we have two models we cover in this unit, which is the wave model of light and the particle model of light. So firstly, we focus on the wave model of the light. So the evidence that suppose the light behaving as a wave, we done the interference thing, we done deflection, we done the polarization. All things are evidence that the light is behaving as a wave. All through, we cover the reflection and refraction in the wave model session. Reflection and refraction can be explained by the both models of the light. So these two things explain the both models. So we also doing that thing, and we do the interference, deflection, and the polarization thing too, which are the main evidence of the wave is the light is behaving as a wave. So firstly, we start with the basis of electromagnetic radiations, that the formula and the things we have to know in this. So electromagnetic radiation, which is the EMR, it is produced through the acceleration of the charged particles. When the charged particle do the acceleration thing, when they produce that acceleration of charged particles, then we have a EMR thing, which is the electromagnetic radiations. In a vacuum, it travels at the speed of light, which is the 3.0 10 raised to power 8 meter per second, which is also the value of the CV of that. So you have to know that in vacuum light travels at the speed of 3.0 10 raised to power 8 meter per second. The universal wave constant, which equation which applies to electromagnetic waves, the only change is that the V we write the C. So C is your speed of light, F is a frequency, and then you have a wavelength. So this is the main formula which you have to know for this unit, and this is the for unit. This is the formula for the your EMR. So frequency. So when we recall the frequency, so we have to know the definition of the frequency for these type of questions when we're doing that. So the frequency of the wave represents the how many complete cycles they per second, and the wavelength is the distance covered in a complete cycle. So how many cycles in per second the wave doing is called the frequency, and the distance covered that to complete that cycle is called the wavelength. So frequency and the wavelength are the very important terms you have to know, because the formula is all about this. And sometimes in questions, they don't directly give you the frequency and wavelength, they give you like that of thing that the number of cycles that per second is that. So this is the frequency, this different. That's all small things you have to know in this. Then we're doing the spectrum thing. This electromagnetic spectrum is very important. Again, you get one question for sure that which classify the electromagnetic radiation in that range. So when we want to look all types of electromagnetic radiation in terms of the frequency, wavelength, and energy, we will examine what is known as the electromagnetic spectrum. So this is all the spectrum, and we have the wavelengths, we have the frequency in hertz, and there is a visible light over there, which is white light. And you have to know main things. We have a mnemonic for this. The radiant Martins invaded the Venus using X-ray guns. This is a mnemonic for to doing from the lowest to the highest frequency and energy. So if you want to go from the lowest to the highest frequency and energy, so we have to deal with the mnemonic, and you can switch this in backwards if you want. So when you switch backwards, so you get the lowest to highest wavelength, which is the from gamma to the radio waves. So that type of thing you have to know, that mnemonic is from the lowest to highest frequency. If you want from the lowest to highest wavelength, so you have to read from the backwards. So this mnemonic is very important. You have to know this mnemonic for your diploma. You get one question for sure. And you have to know some ranges too, of like radio TV is from 10 to 10 raised to minus 10. Somewhere that range you have to know. So then we had doing the Michelin experiment, which is again very important experiment, that some small things you have to know in this too. So in Albert Michelin experiment to determine the speed of light, this all experiment is to find the speed of light. There's a number of scientists, or you can say the physicians, which are doing the experiments to calculate the accurate speed of light. And this is one of the experiment which is very well to calculate the and to determine the speed of light. So they place the two mirrors, one is stationary and one is rotating. You see that one is the stationary mirror and one is the rotating mirror we have. And this is the eight-sided mirror and we have like a octagon shape. The idea that the light that travel from the eight-sided mirror to a stationary mirror back in time, it to take for the eight-sided mirror to complete 1/8 of rotation. So that's all explaining the how the mission experiment and work. But you don't know about like too much in that depth. You have to just know that they're doing the experiment where they calculate speed of light with the eight-sided mirror. That you have to know. And when they complete this one rotation of the angle, so they complete only like about 1/8 of rotation. So the 1/8 of rotation is the main thing you have to know because we use that in questions when we given us that questions. So to the time to for the time to calculate the mirrors was this delta t 1 t upon 8. You can find from the 1 upon f, or you can do the 1/8 of the period, which is the f is again, which is frequency. So the delta t can be find that, and we know how to solve these questions. So you can check the playlist of this unit and the diploma questions also. We covered those whole things. I put the link in the description too. Be careful that when calculating the time from a frequency period, this is represents the time to travel from the eight-sided mirror, stationary mirror, so you must double the distance. So at the end, you have to must double the distance. If you find in the calculating the time from a frequency, so at the end you have to double the distance. Every distance is given, every distance you have to find, so at the end you have to divide by 2. That's small things you have to cover. So this is very important. You get one question for sure in numeric or MCQs. Then we're doing the law of reflection, which is again very important, which is easy topics, that the angle of reflection is equal to the angle of incidence and is in the same plane. Same plane means that this is the plane mirror and this is the incident ray, and they made the angle over there. This is reflected, they made the angle over there and made the normal thing. So which means the angles between the angle of reflection is equal to the angle of incidence as it is in the same plane. So all thing is in the same plane, which is the reflecting surface. So incident theta is equal to the reflected theta. And there's a definition which is like a, in the other words you can use this thing, but if you want to detail things, so you can use this, that the light rays that are incident upon a reflected surface with angle theta with respect to the normal will be reflected away from the surface with the same theta with respect to the normal, called the law of reflection. But you don't know in so much light writing, you have to just know the straight thing that theta incident is equal to theta reflected. All is in the same plane. That all you have to know. Then we cover the curved mirrors, the ray diagrams, but you don't get directly to draw the ray diagrams. But in the like mathematical analysis of the mirrors or the lenses, you have to draw the diagrams sometimes to have your convenience. So you get one question for sure to make the diagram for your convenience, but you have to just know for the to do the MCQs for these questions. Concave mirror, you know, it's sometimes called the convergent mirror, and the type of mirror causes the parallel light rays to converge and then reflected from the mirror's surface. So this is the concave mirror, and the convex mirror is the diverging mirror type of mirror that causes the parallel light rays to diverge after reflecting the mirror's surface. That all stuff we covered already. So main thinking that in the concave mirror we have one special case which made the virtual upright enlarged image. So that are characteristic virtual upright and enlarged. This is special case in concave mirror only. Otherwise we have a different, we have always have a real image. In that case only we have a virtual image. And in convex mirror we always have the virtual upright and diminished. Diminished means small, enlarged means very large. So that all terms we already discussed. You can check this video, check this lesson and get to know more about this topic. You don't know how to make ray diagrams, this is not very good, but you have to know some things, that how the rays can be drawn in the mirror and the lenses. They are separate concepts. Then we have a mirror equation which we use for the lenses too, for the mathematical analysis, which is the 1 upon do plus 1 upon di is equal to 1 upon f, which is the focal length. This is the focal length. Di is the distance of the image and do is the distance of the object from the mirror, both from the mirror. And you have to know this mirror formula, which is very important to calculate the lenses questions or the mirror questions. You get one question for this sure in both. Then we also cover this secondary equation. Again, this equation is same for both the lenses and the mirrors. So hi upon ho is equal to minus di upon do. Then this thing is also equal to the magnification. We discussed that earlier. So this whole thing is equal to the magnification, which is denoted by the m. So if you want to calculate the ho and you have a dido and hi, so you can use this much of an equation. You can't derivate it because both three things are equal to each other. Hi is the height of the image, ho is the height of the object, dido you know. Don't forget this negative sign. This negative sign is in the formula, so you have to know. Then the sign convention. The sign convention is a little bit different in the mirrors and lenses. In the mirrors, if you have a positive, so di is positive, you get the real image. If your focal length is positive, you get a concave mirror. If you have a concave mirror, so your focal length is positive. If your hi is positive, so you get an upright image. And for negative, you get the di is virtual, and focal length is convex mirror. Focal length is negative, you get a convex mirror. Then hi is negative, you get the inverted image. DO is always positive because it is real, so DO is always positive as a object. HI has the relative to orientation, so that's thing you have to know that HI is greater than 0. You have the same orientation of the object as the mirror, and if you have a HI is less than 0, so image and object have the opposite orientations, they have the opposite things. The sign of HI is nothing to do with the image is real or virtual. The HI is not doing with anything with real or virtual. You have to find DI for this. If DI is positive, you get the real image. For negative, you get the virtual image. HI is for the image, like what type of image you get, upright or the inverted. That's all we have mentioned in this. This is something same. So as I told you, that magnification is equal to that all thing. So you can use any of the things that if you want from m is equal to minus di upon do, so you can use this too. Then you have to know this, that sometimes that of question maybe you get, but you have to know this, that if m is less than 1, you get the diminished image. M is equal to 1, you get the same image, which is the same size image. If it is greater than 1, you get the enlarged image. The negative sign is required in above equation for the magnification to be consistent with the signing convention. So that's why this negative sign is very important. All things are same in the lenses. So reflection is again very easy topic, but you have to know the things in that too. So when light travels between a different media, like from water to air, so you get a light wave changes. So if you have like something like this is like water infiltrated, the weight goes over there, and you get a little bit like a tilt image like that, and there is a normal, that all thing is called the refraction thing. So the which experience a change in wavelength is known as the refraction. When the light wave goes from the one media to another media and they change in speed, they experience the change in wavelength, then this is known as the refraction. One point to recall in that the light travels between different media, its frequency remains constant. Frequency remains constant in the both medias. The wavelength and the speed can be changed. One thing in that this thing that when light travels from a medium of low index of reflection, if you have a low index of reflection in one media and it travels from the low index of reflection to the high index of reflection, the light will bend towards the normal line. So light will bend towards the normal line, but if the light travels from the media with the higher index of reflection to the lower index of reflection, so the light bends away from the normal. So we get the away from the normal line, and we got the towards the normal line when it goes from the lower to high. That small things in reflection you have to know. In Snell's law, you have to know just one formula, this one, that n1 times sine theta 1 is equal to n2 sine theta 2. The n1 is the index of reflection of the incident thing, the 1 is not about the incident, 2 is not for the refraction thing, which is the reflected medium. Then sine theta 1 is the index of reflected to a normal line, this angle of incidence. Sine theta 2 is angle of deflection to a normal line. Both should be in degrees, and the n index of reflection are no units, so this should be like the same thing. The above equation is called the Snell's law, and you can also write it like this. This is like a further version of this where we include the speed and the wavelength. So when the speed and wavelength can be included in that formula, you will get a very big formula like this. Again, that two things are reflected, the two things are all the reflected mediums, and the one is not all the incident mediums. So the formula is like that, and make sure the wavelength should be in meters. your speed should be meter per second, and the n has no units. So you can use any set of this. You can use this and thing with the wavelength, you use velocity with and you can velocity with wavelength. Everything can be fine. This was convenience. Then we cover the total internal reflection thing. Total internal reflection thing is again very important thing that when we say about the critical angles. Why we consider that? So if the angle of incidence is greater than the critical angle, which is theta c, the light will be reflected into the incident medium, no reflection will be occur. This is called the total internal reflection, which is TIR. So when the total angle of incidence should be greater than the critical angle, which is theta c, light will reflect into the incident medium only. The no refraction can be occur in that case. That's why we take this as a total internal reflection thing. So this happens when the angle sometimes achieves a special value which is known as the critical angle, and critical angle is equal to the theta 1, and your theta, if you find the critical angle which is theta 1, you have to work for theta 1, and at the end you can say that theta 1 is equal to critical angle, which is you have to find. So the theta 2 is not given in that question, so theta 2 you automatically get with is 90 degree. Because there is no refraction occurring, that's why the angle stays 90 degree. So they made a perpendicular thing. The total internal reflection, the index of refraction will same as the of incidence, consistent with the law of reflection. So I have to say with the law of reflection, and the principle of this is the optical fibers. Sometimes they use the word optical fibers for this topic. So you have to know this is like just the application for the internal reflection, which is the optical fibers. Next thing we have a dispersion and recombination. Again, easy copy when the white light goes into the rainbow colors. So the wall opposite of the oncoming beam, the notice that we have a spectrum. So spectrum is the band of colors, and they set from the lowest to highest frequency or from the highest to lowest wavelength. So red, orange, yellow, green, blue, indigo, and the violet. You have to mnemonic for to memorize this, which is the rho GB, which is the name of the one person. You can know that red, orange, yellow, green, blue, indigo, violet. From red to violet, you have from the lowest to high frequency, or you can say you from the highest to lowest wavelength. So both things are different. So from here you can say that red has the low frequency and violet has the highest frequency. Red has the highest wavelength and violet has the lowest wavelength. And the things we have to do. They only like ask about the red and violet sometimes, like frequently. Then we have a thin lenses. So lenses are as I told you, the lenses are the same as we did in the mirror. So I quickly do this topic. So the convergent lens, or we can say this is a convex lens. The other name for convergent is convex lens. Other name for divergent lens is the concave lens. Convergent lens refracts rays traveling parallel to principal axis and inward to intersect at the principal focus, to on the other side and intersect from the principal focus. So reflects rays traveling parallel to principal axis outward to appear as through they originate from the virtual principal focus. So divergent lens made the virtual images, and the convergent lens made the real images. We have the special case again in convergent lenses, which is the virtual upright and large image we get when we between the focal point and the vertex. Divergent lens we always get the virtual upright and diminished image. So again, the radars are not very important. They not directly ask you to draw. You have to draw for your convenience. Then there's the same thing. Then the mirror formula is same. Then the HI upon HO, DI upon DO minus DI upon DO is the same in that case. Difference is that we just do this thing. That if the focal length is positive, we get a convergent lens. If focal length is negative, we get the divergent lens. That all things stays the same. The HI stays the same. The DI stays the same. All things stay the same. Just we do the lenses topic now. Then we have a diffraction. The topic which is again very important when we do screen things. We do the two formulas in this, general equation and the small n approximation. So you have to know this something about this too, and which is very important for the your diploma. You get one question for sure again. So here one formula is skipped, that the tan theta is equal to the x upon f. Okay? So when light encounters a slit, and or a barrier, it will spread out in passes through the slit or a yarn or around the barrier is called a deflection. So there's all the slit and the barrier thing. When they stuck in that, it count as that, and they passes through the slit and around the barrier, you will tell that this is the deflection. You don't know more about the deflection part, but you have to know something for the deflection, which is the Young double slit experiment, which is very important experiment, and this experiment can be done with the two formulas. If your tan theta is greater than 1, so you have to use this formula. If it is less than 1, so you can use this thing. So if it is under 10 degrees, so you can use this thing. If it's not, so you can have to use this. So this d is all the distance, and theta is the angle of the angle of the slit they made, and the n is the nth fringe. No units they have. HDNL, you have to know this lesson, and this lesson has a more like a broad topic. I made the full-fledged 2 parts of this. You can watch this video, and I put the link in the description. So this is very important topic. You get the 1 question for sure. Then we have to carry this out by the particle model of light. We done the wave model of light. They are all topics in the wave model of light. Now we're doing the particle model of light and all the topics which are involved in that topic. So the evidence putting the light beam as a particle, we do the photoelectric effect. We do the quantum effect. Before we examine these effects, we want to discuss more about the particles of light of the photon. So what is photon? So photon is the represents by the quantum of light. It is a particle represent the smallest energy unit of the light. This is the smallest unit of light, and the photon topic is very important. You have to know the Planck's equation. The E, which is the energy of the photon, is equal to the h times f is equal to hc upon wavelength. That h is the Planck's constant, and this has some value. These are 2 values basically. We have a 6.63 into 10 raised to power minus 34 joules per second. If you have an EV dot second, so you have to use 4.14 into 10 raised to power minus 15 EV dot second. These are the 2 values you have to know, and you have to use that by your convenience which you want. Then we do the photoelectric effect, which is the more like a theory part, and in theory part we cover that what is photoelectric effect. So when the high frequency EMR is shown on the metal cathode, the electrons, which are basically the photoelectrons, are emitted. When they are emitted, they travel to the anode. And then they register the photocurrent measured by the emitter, which is called the photocell, and that whole process is called the photoelectric effect, which is done by the Hertz in 1887. From here, we are discovering the minimum frequency. If there is a minimum frequency, you have to determine the minimum frequency. So you have to find the threshold frequency, which is F0, like this. So incident radiation below this threshold frequency will not cause the emission of the electron. There is some more in this, and we cover that more all things in the topic of the photoelectric effect. So you can watch this lesson too. But for now, you have to show for the one shot. You have to know about these much things only, because there is only like a broad topics. So we small that topic, we do some brief conception of this. Then work function. Work function formula is very important. If you want to know the work function with the threshold frequency and the Planck's constant, so we have to use this function, that W is equal to the H times threshold frequency. If you have to find you have a kinetic energy, you have a maximum kinetic energy, you have to find the maximum kinetic energy. So make sure you use this formula. That the very important questions are made from that topic, and the total photon energy is from here. If you find the number of photons which are made, so you can use this formula to know this. How can we calculate this? This is this topic. For now, all formulas are not on your formula sheet. You have to memorize this. Make sure you memorize this in your diploma. Next, we do the quantum equation. So quantum equation is in your formula sheet, but this thing is not in your formula sheet. When we're doing the scattered photon wavelength is minus the incoming photon wavelength. In this formula, I have to know that the delta wavelength is equal to h upon mc times 1 minus cos theta. All things are labeled in that. You can take a screenshot if you want. And yeah, quantum effect is again very important topic, and you have to know the calculation, and you have to know this formula. This formula is not on your formula sheet. Last topic we cover is the wave particle durability, where we do the photon momentum thing. So there's also a photon momentum. So photon momentum thing is very important, and the wave particle durability, which they say is that the photoelectric and the quantum effect demonstrate the light had behave like particle-like properties, and also the light had wave-like properties in the diffraction polarization interference. So we mean that the wave particle durability means that the light is neither a wave nor a particle, but either it is a both. It's not a particle, it's not a wave, but it's the both. Depends on how we absorb it, decide to interact with it. With that, we denote this formula, which is wavelength is equal to h upon p, which is the last physics principle 9, no, the second last, I think, 9, which is the wave particle durability formula. And this is the physics principle. P is the momentum, and h is the Planck's constant, and your wavelength is the wavelength. Make sure your Planck's constant should be this only in that question, because you deal with the joules per second, so this stays the same. So this is the wave particle durability, and very important topic again, I'm telling them. So now we have some questions we have to cover, and some practice questions we have, which are very important. So we get the question from Michelin type experiment. So Michelin type like experiment, the two mirrors are rotated 4.7 km apart. If the speed of light is 2.9 10 per 8 meters per second, determine the frequency of the rotation of the 10-sided mirror. So they changed the question. We're always doing the A-sided mirror emission experiment, but there is the 10-sided mirror. So how do we deal with it? So in this question, we have a distance given. So if the distance is given, so we have to multiply it by 2 first. So delta t is equal to multiply by 2 multiply by 4.7 kilometers. In this, you will get about 9.4 kilometers. Now you have to find a frequency, so we do some backward thing. So in that case, if you know your v is delta d upon delta t, you have v. So you can find the delta t from here. This is delta d upon v. So 9.4, you have to count this in meters, so you have to multiply this by 10 raised to power 3 meters. Divided by the time, or divided by the v, we have a 2.9 to 10 raised to power 8 meter per second. You get to a delta t of about 3.2414 into 10 raised to power minus 5 seconds. But you have to find the frequency. For frequency, you know this is a 10-sided mirror, so your delta t should be equal to 1 upon 10 times t. That t is equal to 1 upon 10. No. This t is equal to 10 times delta t. So 10 times delta t, 3.2414, make sure you use the non-rounded value. You get your answer about 3.2414 into 10 raised to power minus 4 seconds. Now, last thing, you know the frequency is equal to the 1 upon t. 1 upon period you want to say if you want. This t is throughout the period, but they have the same units. So you have to do 1 divided by 3.2414 into 10 raised to minus 4 seconds. You get your frequency of 3.085 hertz, which you can write it as 3.1 into 10 raised to power 3 hertz. So that's how the backward thing works. And in this, you have a 10 centimeter, so make sure you use the 1 upon 10 times the period. That small thing is the matter, and sometimes just trying to use the 1/8 in that question. So make sure you use 1/10. Let's do the mirror question. An object is placed 21 centimeter in front of the concave mirror. The image is real inverted and 4.0 times the larger than the object. So to determine the distance and the focal length of the mirror. So the 21 centimeter is your DO is given, and this 4.0 times the larger than the object, which means this is the magnification, and there's inverted. And if there's inverted, so magnification should be in negative. So it's minus 4.0 with no units. So that small things again matter. If there's inverted, you have to read question carefully, then magnification should be negative with no units. So you find the distance, so you know the magnification is equal to minus di upon du. You know this. So di is equal to the minus m times du. because we find the DI first. So DI is equal to minus 4.0, DO is 21 centimeter, and you get minus positive, you get 84 centimeters. And we show that this is the real image because you're getting positive, which is right. Now you have to find the focal length. So you know 1 upon f is equal to 1 upon DO plus 1 upon DI. So 1 upon f is equal to 1 upon 21 centimeter plus 1 upon 84 centimeter. You will get 1 upon 21 centimeter plus 1 upon 84 centimeter whole raised to minus 1 because this goes to f. You solve this whole thing, you get 16.8 centimeters, which is basically the 17 centimeter. So you will get a focal length which is greater than 0, which means this is your concave mirror. This also says with that this is real and inverted. If it is a real, so you have a concave mirror. So that's the focal length you find, and that's the DA you have to find. And you can check this by this is a real and the concave mirror. So the question is right. So that type of question you get, it's a simple question, sometimes the more like something tricky in that, but that. Next we have the question says the index of reflection for the medium A is 1.92. The speed of light in medium B is 2.50 10 raised to power 8 meter per second. We have to find the critical angle AB interference. So what things I've given? We have an N1 which is A, medium A, which is 1.92. We have to find the N2, but because for critical angle we have to find the N2. We don't have the N2. So theta 1 is equal to theta C. So theta C is equal to, you have to find theta, you have to know this in 90 degree because this is a critical angle question. And we have a speed for medium B, which is the V2, you can say. We have V2 or you can say VB. This is 2.50 10 raised to power 8 meter per second. Our goal is to firstly find the N, which is the index of reflection. So let's find the index of reflection for B. C upon VB, you can use the 2. So VB is equal to C is 3.00 10 raised to power 8 meter per second. Velocity is 2.50 10 raised to power 8 meter per second again. So you get VB of about 1.20. Now, you know N2 upon N1, you use a Snell's law part, which is equal to theta 1 upon theta 2. You have to find this thing, which is this thing. Theta 1 is equal to theta C. You can isolate this thing, and you get this upon N1. So sine theta C, or you can isolate this thing, sine minus 1. So N2 is 1.20, sine of 90 degree upon 1.92. So when you calculate this, you get 38.628 degrees, which is equal to the sine theta 1, and you find the critical angle of 38.7 degrees in 3 seconds. So in one question, you use index of reflection formula and also use the Snell's law. So that type of question which covers the 2 topics or 3 topics can be given in your diploma. So I have to do practice of these type of questions too. Next question is from the lenses. An object is placed 17 centimeters from total diverging lens. Imagine this is a diverging lens. The image height is 20% of the size of the object height, which is that HI is equal to 0.20 HO. Determine the focal length of the lens. So sometimes when they made the question trickier, so they mention like that 20% of the size of the object height. But they're given in the bracket, sometimes they're not given in your bracket in diploma. So you have to know how to deal with this. So they given you the DO. So DO is given, and they also mention the HI. So in this, HI is this, and you find the focal length, which is F. Basically, you don't have anything, but you start doing something. So M is equal to H by HI upon HO, you know that. You know HI is equal to 0.20 HO upon HO. HO and HO cancel out. You will get your magnification of 0.20. From where you can find the DI. How? You know this is equal to M is equal to upon DI DO2 also. So minus di is equal to the magnification times do. So di is equal to minus magnification times do. So di is equal to negative 0.20. Do is 17 centimeters. You will get your di of about minus 3.4 centimeter. This is diverging. So you get the upright image. That's why we get the negative. Now 1 upon f is equal to 1 upon di plus 1 upon do. So 1 upon f is equal to 1 upon di is minus 3.4 centimeters plus 1 upon do is 17 centimeters. So when you calculate this out, you get a negative 1 over there and you get about minus 4.25 centimeters, which is 1 minus 4.3 centimeters. This is negative, which means this is the diverging lens. So you get your answer. You have to use the three things and get the answer. And so that's why these questions are very important. This kind of questions are very important for your diploma point of view. We have another question to cover. So a question says, a light radiation with the wavelength of 470 nanometers is shown through a diffraction gradient that is 36 centimeters from a screen and the distance between the maxima is 11 centimeters. Determine the distance in meter between the slits. So the conversion questions can be done. Firstly, you have to find the angle. If the angle is greater than 10, so you have to use the general formula. But if not, so you have to use the small formula if you have. So what things we have given? So we have 470 nanometer, which is the wavelength. Diffraction gradient 36 from the screen. 36 is given the L. So this is L given. Distance between the maxima is 11, which is the X given. Determine the distance. Distance we have to find the D. So first get the angle. So tan theta is equal to x upon L. Theta is equal to tan minus 1. X is 11 centimeter upon 36 centimeters. So theta is equal to 16.991 degrees, which is greater than 10. So you have to use the general equation. You have everything else, you find a d. So n times wavelength upon sine theta. So d is equal to 1. N is not given, so we take it as 1. Wavelength is 470 into 10 raised to minus 19 meters. And divided by the sine of 16.991 degrees. Make sure you use the non-rounded value. When you calculate this, you get about 1.608 into 10 raised to power minus 6 meters. You have to convert micrometers. So 1 micrometers is divided by the 10 raised to power minus 6 meters. You get your D of about 1.6 micrometers in 2 seconds. So that's your answer, and this question is very important because this covers the general equation and the concept of the small angle approximation that you have to know that 10-degree thing. So that's that's all for this, and this is the unit C one shot, and we complete their unit C2. So I skipped there some copies of the practice for. So if you want for practice question, you can check the playlist. I will put the link and you can check the diploma questions, practice questions. You can cover those and you can watch the lessons separately. So that's all for this lesson. Language where EduVibe learns but not harder. Please like, share and subscribe to my channel. If any questions, let me know in the comment section. All the best for your diploma. See you in the next lesson. Till it's native with EduVibe.